Mr. Klein here with our video on kinetic energy. In this video we're going to describe what energy is, what exactly kinetic energy is, how to calculate it, what influences it, and how to graph it. And I can't think of anything better to get started by discussing kinetic energy than an explosion. Now, explosions have lots to do with energy. I mean, without energy, explosions wouldn't occur, and we wouldn't want that. So what we're going to do is let's just dive right in. Let's talk about what is energy. Whenever we discuss motion, we remember that energy is required for motion to occur. But what is energy? Well, energy is it's a thing, but you can't really feel it or something like that. What it is, it's the ability to do work or to cause change, or even more simply, the ability to do work, because work changes things. So for example, if you want a baseball on a t-ball stand to move, what you're going to have to do is you're going to have to transfer energy to it through you swinging the bat and having the bat make contact with the ball. So the only way a baseball is going to fly is if the bat hits it or you throw it or something like that. Energy itself, we can measure the amount of energy an object has. And that is with the metric unit of measurement that we call the joule, Joule. It is named after a scientist, so it's not like a pretty diamond or something. It's named after an old dead guy. A joule is the amount of energy needed to apply 1 Newton of force over the distance of 1 meter in 1 second. Okay, so you have your graphic organizer, so let's go ahead and start it. So we have right here is energy. Energy is the ability to do work and cause change. And in our next section, we're going to talk about what exactly the two forms or classifications of energy are. So energy can take many forms. However, all energy, no matter the form it takes, can be classified into 2 general categories based on how it's being used. The first one is kinetic energy, or the energy of moving matter. That's the energy in things that move. So if an object has kinetic energy, then work is either being done by it or to it. So as we can see this dog sliding across the ice, we can see that energy is being used because the dog is moving, sliding, attempting to walk on the ice. Poor puppy. Being done to it. Okay, so the next one is potential energy. Potential energy is essentially the energy that's stored inside of matter. It's not being used, it will be used later, but it's waiting there. It is the energy that an object has depending on its position or its shape. So for example, this cute and cuddly panda, hang on buddy. This panda bear has potential energy while he's hanging on until he lets go and gravity pulls him down. From there, the energy is turned into kinetic energy. So let's go ahead and let's fill out our graphic organizer. So we have potential energy, which is stored. Our next lesson is going to concern potential energy. So from here on out, we're just going to focus on kinetic energy, or the moving energy. And in our next section, we're going to talk about what actually influences the kinetic energy of an object. Kinetic energy depends on 2 factors, okay? And that is the mass of the object and the velocity of the object. Now, much like force and momentum, increasing or decreasing the mass of the object does the same to the total amount of kinetic energy. In other words, you increase the momentum by increasing the mass, you increase the kinetic energy. However, unlike momentum, because momentum has velocity, remember, and force has acceleration. So remember, acceleration is a change in speed or direction. So we're only talking about whenever we have velocity going in there. So unlike momentum, changing the velocity of the object has a much greater impact on the total amount of kinetic energy, because a force is far more efficient in adding velocity to an object already in motion than it is to get moving from being at rest. So for instance right here, okay, there's not a lot of motion here with the little kitty cat knocking over the bowling pins, okay? Not a lot of mass, and so it's increased, and also the kitty isn't going too quickly. However, if you add some velocity, like this poor guy, whoop, okay, there's a whole lot more kinetic energy because he's whipping that ball a whole lot harder than that kitty cat was knocking over the bowling pins. So let's go ahead and let's add this to our organizer. What influences kinetic energy? Well, mass and velocity. And remember, velocity impacts kinetic energy way more than mass does. And in our next section, we're going to actually learn how to calculate this in order to get a number showing how much kinetic energy an object has. So if you have mass and velocity, calculating the kinetic energy of an object is actually really simple. You use the following formula. Ke equals 0.5 mv squared, or kinetic energy equals the mass times its velocity squared. Okay, now I know some of you, your brains might be melting, so let's go ahead and let's do a sample problem here. So Maddie and her bike has a mass of 45 kilograms total. She's riding down the road at 6 meters per second. how much kinetic energy does Maddie and the bike have? Well, remember, when we do problems in science, the first thing we do is we figure out which formula we're going to use. We know that kinetic energy equals 0.5 times mass times velocity squared. That's what we want to find out, the kinetic energy. So what we're going to do is, now that we have the formula, we're going to substitute the letters for the numbers. So M is for mass, okay? So 45 kilograms was the mass of Maddie and her bike. And how fast is she going? 6 meters per second squared. So in order to do the math here, we need to remember order of operations. Okay, you start, I know I put some parentheses, but that's just showing you that the mass is 45 kilograms and the velocity is 6 meters per second. But the first thing we do is we square it, because remember, exponents come first in the order of operations in this equation. So what we do is we square it, and we end up with 0.5 times 45 kilograms times 36 meters per second. Because 6 squared, 6 times 6 is 36. From here, we just go on out multiplying. So we multiply 0.5 times 45 times 36, which gives us the answer of 810 joules. Remember, the joule is the metric unit of energy. So that's the answer. And for those of you who might be confused, like Mr. Klein, why is there 0.5? Well, 0.5 is a constant. We know that every single time we do a problem involving kinetic energy, we have to use 0.5 in our calculation. The M and the V for mass and velocity are variables, because it depends on what problem you're doing that the variable is going to be for the mass or the velocity. Those numbers can change. 0.5 doesn't change. The fact that you square the velocity doesn't change. So that's how you go ahead and you do this problem. As you can see, increasing the velocity, this is an important thing. Increasing the velocity of the object does more to increase the kinetic energy due to the fact that it's squared in the equation. You know that if you increase the velocity, you're going to increase it a lot more. So let's go ahead and fill out our graphic organizer, okay? We put the formula, kinetic energy equals 0.5 mass times the velocity squared. And in our next section, what we're going to do is we're going to talk about how we can put these numbers on a graph and we can visualize how this growth in velocity and growth in mass affects the kinetic energy of the object. So in graphing kinetic energy, you see it doesn't form a line if you increase the mass or the velocity like a straight line. Rather, it's a curve. And this kind of curve is what we call a parabolic curve. And it occurs because the formula for kinetic energy, 0.5 times mass times velocity squared, that squared, it being an exponent, creates the parabolic curve. Remember, before we go into some graphs and looking at this, because you squared the velocity, the curve becomes steeper when you increase the velocity than if you would just increase the mass. And if you're like, Mr. Klein, this makes no sense, I don't see any graphs. So what I decided to do was do a numerical experiment for you. I got 2 sets of masses, okay? So I have 10 objects. They range in size from 1 kilogram to 10 kilograms. The next set of masses ranges from 2 kilograms to 20 kilograms, and they increase in 2 kilogram increments. So instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I increased it 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I made them both, as you could see, go at the same speed. So 1 kilogram and 2 kilograms both go 1 meter per second. And I did that all the way through, and I figured out the kinetic energy for them. And what I did was I put them in a graph. As you can see, my first set, the ones that went through 1 through 10 kilograms, went up in the parabolic curve. But you see, if I increase the mass, I got a difference of 500 joules. So whereas at 10 kilograms, it goes 500 joules worth of energy, 20 kilograms would give you 1,000 joules of energy going at 10 meters per second. Okay, so that's what happens if you increase mass. And as you can see, I also changed the velocity. So what I did was I changed the velocity but kept the mass the same. So I took the same 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 kilograms, and then what I did was I made them go at different velocities. So I took a 1 kilogram weight, made it go 1 meter per second, figured out the kinetic energy. Then I made it go 2 meters per second, and I figured out the kinetic energy. And I did that, and then I put it in a graph. And as you can see, it's a difference of 1,500 joules. If I put 10 kilograms going 10 meters per second, and then I doubled the velocity up to 20 meters per second for 10 kilograms, got a 1,500 joule difference. So as you can see, increasing velocity does a whole lot more to the graph in terms of increasing the curve than it would just increasing the mass. objects. So there you go. That's your lesson on calculating kinetic energy. We defined energy, we classified kinetic and potential energy, and from here on out, we talked about how mass and velocity affect the kinetic energy of the object. We learned how to calculate it, and then we see right here how we're able to graph it and see how the changes in mass and velocity affect kinetic energy of objects. You understood this lesson. Hope you learned something. And if, as always, you have any questions, please let me know, and thanks for watching.